Hello. Now we're going to work with Lecture 9, Tracking and Parameter Estimation Techniques in the Introduction to Radar Systems course, and this is part 1 of that lecture. Here's our generic radar block diagram again. We're going to show you what the area of the radar we're going to be studying. After we've gone through the receiver, signal processor, and we've detected the targets, then we want to get the best estimate of the observables that we've measured, the range, the azimuth, the Doppler velocity, etc. And that's called parameter estimation. And then we want to correlate those detections and those best estimates from scan to scan and get them all lined up, so see which ones belong to the same physical object in space and form what we call a track. And again, improve the estimate over and over as we increase the track length. And that's what we're going to be talking about in this lecture. So now let's move on. All kinds of radars. In fact, just about every radar has this function. Be it ground-based range tracking radars, radars that track ballistic missiles, air traffic control radars, radars on ships that do air surveillance. They all perform this tracking function. And you see some of these radars are phased array radars, and some of them have mechanical scanning dishes. This particular radar is a combination of an electronic scan and a mechanical scan in azimuth and elevation. It's a lens radar, and it has tracking techniques within it. They're a little different from others, but they all perform this tracking function. And you're going to learn how the tracking function and the parameter estimation function differs in all of these different radars as we go through the lecture. Okay, well, what are these functions that we do? So after the target's initially detected, there are a number of things that the radar has to do. We have to continue to detect the target, and once we detect the target, we want to make the best estimate we can of the target parameters from the observations we've made with the radar, position of the target, its size and motion, etc. And then we want to associate the detections with a specific target. Are all these detections from the same target, or are they from different targets? We're going to use our measurements of range, angle, and Doppler to do that. And then once we start to get an idea of not just where the target was, but from looking at a number of detections from a specific target, where it's going, we want to predict where the target will be in the future so that we can take detections that are close to where the target's going to be in the future and associate them with the target. And we're going to use multiple observations that we've accrued to develop a very good so-called filtered estimate of the observables of the target track as a whole. Okay, here's an outline of what we're going to be talking about today. You see there's a number of different topics in parameter estimation and then tracking. We're going to focus on range estimation, angle estimation, particularly the technique called Monopulse, and we're going to look at estimation performance. How well can we make those estimates in angle and in the various observables? And then we're going to look at Doppler velocity estimation, then continue on to tracking and summarize. Now let's move up to the estimation and go over that area in detail. Okay, so what are the things that we estimate when we have a radar antenna that puts out a beam, sends the energy out to the target, it comes back? What do we measure? Well, we measure the target's location, its azimuth and elevation angle from where the antenna beam is pointing, and from the time delay that it took the echo to go from the radar out to the target and back, we measure its range. From the size of the return that we get back here, we measure the amplitude of the target and can make an estimate of the radar cross-section. If the radar is very well calibrated, we can make an estimate of the radial length of the target if we have sufficient accuracy in range or high enough bandwidth. And we can measure the cross range through Doppler estimation techniques and imaging techniques, which I won't get into right now, but we can estimate the size of the target. We can also make estimates about the target's motion. Direct measurements of the target's radial velocity come through the Doppler effect. We talked about that earlier. And from looking at our measurements and how the radial velocity changes over time, we can measure the radial acceleration, and then implicitly through calculations, and from these other data, we can calculate the rotation and precession of the object if it's a rigid body, and measure it if it's in the atmosphere, its ballistic coefficient. That's a measure of the drag that it has. It's a measure of the cross-sectional area of the target and its mass and other attributes. Okay, with respect to parameter estimation, how do we get good range, angle, and Doppler velocity? Well, the range is inversely proportional to the bandwidth of the pulse. It's proportional to the pulse width. So if we have very high bandwidth, then we'll have very good range resolution. And commensurate, if we have very narrow pulses, we'll have good range resolution. Excuse me. From the size of the angle beam, that will determine to a great extent our angular accuracy, along with the wavelength of the radiation. The beam width is lambda over d, remember from our antenna lecture, and the Doppler velocities is our measurement resolution is proportional to the wavelength and inversely proportional to how long we coherently integrate. So if we have a given wavelength radar and we coherently integrate a long time, we'll get very good Doppler, very small Doppler resolution, very good Doppler resolution. And each of these resolutions, the accuracy improves significantly as we increase the signal-to-noise ratio. And the accuracy is proportional to the resolution, quantity up here, divided by the square root of the signal-to-noise ratio. And that would be in natural units, not in dB. The basic overall approach that we use is we look at overlapped measurements. And we do range splitting, what you'll see a lot more of, and I'll describe later, monopulse techniques, and Doppler filter or bin splitting. We look at the target with the range cell set in one location, the range cell set in another location, slightly overlapping measurements, and we look from looking at those differences in the measurements, we can see where within the range, angle, or Doppler cell the target really is, and that's how we hone in on its accuracy of the measurement. First, let's look at range estimation. When you see a target, you just don't see it in one range sample cell. You see it in a number of cells. And this shows the response in voltage out of a matched filter that we get from an echo, from a simple CW pulse. And we see at these different little X's, the voltage output, they'd be our time samples, if our time samples were at these locations for that pulse. Now here's the true target location, but our samples are off somewhat. And if we just looked at where we got the biggest output, our location wouldn't be quite accurate. It wouldn't be the most accurate that it could be. So we can use a number of different techniques. We can take these estimates and fit them to the curve where we know the matched filter output to be. We can take a weighted average, weighted by the output of the amplitude, and see where that would be. That would be very close. And this range accuracy will improve if we increase the bandwidth. Remembering this width of the response in range is proportional to 1 over the bandwidth times 1 over the signal-to-noise ratio, which also implies it'll improve if we have better and better signal-to-noise ratio. So if we want better accurate estimate of range, higher bandwidth, and higher signal-to-noise ratio are a big help. Okay, now what do we do with angular size? And these all go back to that first example I give you. These are examples of why those three quantities, things get better with higher amplitude. Okay, and in this case, in antenna size, it improves with beam width. If you think back to the antenna lecture, if we have a parabolic dish reflector, here's the feed. The beam width is proportional to the wavelength, approximately equal to the wavelength divided by the diameter of the antenna, its aperture, and the beam width in degrees is this quantity times 180 divided by pi. And if we plot over here the half power beam width as a function of the antenna diameter, and if we increase the antenna aperture size, the beam width goes down. So we get better and better beam width if we either make the wavelength smaller or the aperture bigger. And here's this example. In the example, these three lines were drawn for here down for an S-band 10 centimeter radar, and X-band, a 1 gigahertz, approximately a little bit lower frequency than L-band, and then up in almost to the UHF frequency range of 300 megahertz, 100 centimeter wavelength. But you can see as you go a factor of, for a given antenna diameter, if you go a factor of 10 in wavelength smaller, you'll get a factor of 10 smaller in beam width. Okay? Now let's look at angular resolution in a little more detail. And this whole idea, if we take two different looks at a target. Okay? Now say we have located, here we have the antenna main beam response, and we're blowing it up, and we have two angular positions of the beam. One over here, and one over here. And if the target is located in the center, its response that this first antenna will see is a small response from the yellow, from the light-colored antenna, and a large response from the left-hand antenna. And as we move the antenna beam over to the right, you see that the beams get closer and closer and closer together to the where they're equal when the two antennas are directly aligned with the target. And then when they're not aligned, when this one, the yellow one, is aligned exactly with the target and the blue beam is not, you see that it's this would be the response you get from the two antennas. So this means of detection provides a coarse location and angle, and it's we isolated within the beam width of the antenna. We can get typical accuracies on a 1 degree beam width at 100 kilometers will be 1.7 kilometers, and that's huge. So what we need to do is to do angle estimation techniques which give measurement accuracies much greater than the beam width. Now, there are a number of different ways we can do that. One, we can use sequential lobing. Another, we can use conical scanning. And a third, we can use monopulse techniques. And I'm going to discuss them one at a time. First, sequential lobing. Now, with sequential lobing, we take the antenna and we know approximately where the target is. It's located out along this dashed line. That's where the target is located. And we see a visualization of power versus angle here. And here's the target. And we have beam 1 and we have beam 2. And what we do is we send out two beams, moving the antenna slightly to the left of where we believe the target is and slightly to the right. And we do this sequentially at two different times. We reuse the same receiver hardware to make these beams so that you do them one after the other. And the response we get if we were off to the left, actually in this case, if we were off to the right, if the target was off to the right, is we get more of the target amplitude would be in beam 2 than in beam 1. And as we move the beams, the center between the two beams over a little bit, shifting it to the left, you'd have a little less amplitude from beam 2 and a little more from beam 1, and then you do it a third time, and when the two beams are giving equal amplitude, then you know the target is exactly between the two beams. And that gives you do this reiteration with a control loop that redirects the antenna location to equalize the beam response from the two separate beams. And that's how the sequential lobing technique is used to measure where the target is within a beam. Conical scanning works slightly differently. You have, again, a dish antenna typically, and what you do is you take the antenna beam and you rotate it in a circle about the expected location of the target. And so the beam will be rotating about an axis. And it won't be exactly where the target is. And this other line going out from the antenna is where the target is. It's the line connecting the target and the antenna. But you're rotating off that target axis about some rotation axis that you think is near the target, but not there. If you plot the received amplitude as a function of time, you'll get this wavy line for the envelope. And what you'll actually see, is as you rotate the antenna beam will move from here to here to here to here about the target. And if the target will be seen with different amplitude as it rotates. Now, from the phase of modulation of the envelope, that's how this varies, that will give you the angle error that you're off the rotation axis. And the amplitude of modulation gives you the displacement that you're off. So you can find out both the direction and location of this target axis from the rotation axis exactly, and that will give you an exact measurement of where the target is. And if you set this system up with a closed loop control loop, you can move the rotation axis slowly to where you believe the target axis is, and when you have no sinusoidal change in the amplitude, then you know you're right on axis and tracking the target perfectly. And that would be the exact location within the beam that you are. Now I'd like to move to the third technique, monopulse estimation. And monopulse estimation compares two or more simultaneous receive beams at the same time. And this is going to require simultaneous receiver channels to process the data. And what we do is we process the sum and difference of two squinted beams, two beams that are off angle, that are pointed towards the target, and they're used to generate what we call an error signal. I'll go into what that is in a little more detail and later on in the view graph. And that error signal from each channel is going to require a separate receiver. Now, monopulse is an improvement over conical scanning and sequential lobing, and because their performance degrades with time-varying radar returns. And monopulse methods can be made via two distinct ways of measuring monopulse. One, which is amplitude comparison, and that's more normally used, and then a phase comparison monopulse. And we'll describe both methods. And here we see at the feed of a parabolic reflector, 4 different feeds. There's one in the center that was from a different frequency, but we have 4 different feeds The two upper feeds were generated a sum for the elevation, and the two lower ones a sum signal for the going to sum the two upper channels with the two lower channels, and then subtract the two upper channels from the two bottom channels. The reason it's 4 is you can perform the same by adding difference, the side channel and this side channel, and subtracting those two channels. You can perform a monopulse measurement in both azimuth and elevation. Visually, you'll get to see that a little bit later. But the point is that we make simultaneous receive beams we generate. Okay? Now, the pairs of offset receive beams are used to determine the location of the target relative to the bore site, the geometric center of where the antenna is pointing. And we do that by calculating from the sum and the difference channel an error signal. And that error signal is used to re-steer the antenna so that we're exactly pointing the antenna on target. Typically, 2 offset receive beams are generated, and with those, as I said earlier, we generate a sum and a difference, and we use, again, separate receivers for each of these. Now here's what we end up having. We have a target located at the center, and we have 2 separate beams that are generated, one from beam A and one from beam B. And here are those 2 beams. And then we send them into a box called a microwave device called a hybrid junction, which is able to perform simultaneously on the traveling electromagnetic waves an addition of them and a subtraction of those 2 signals. And the addition of the 2 signals we call the sum, and the difference we call the difference. And when they come out 2 separate ports, and we call those the sum channel and the difference channel. Okay? And the difference channel between these 2 beams, because they're slightly different, there'll be a slight dip in the center, and the sum channel will just reinforce because it'll just be a little bit wider but have the same general characteristics and a little taller. Okay. Here are some pictures of what these actual microwave devices look like, and they're rather cute things. I'm not going to get into them in a lot of detail for this particular lecture. There's one they call a magic T, and you can see where in this the waveguide entrance the A channel would go, and then the B would come in here, and magically, as it turns out, it's electromagnetics, Maxwell's equations. Coming out, one end will be a sum channel, and the other end a difference channel, and then there's a 3 dB directional coupler where you can put the A channel in one direction, the B channel in another, and coming out these 2 different ports will be the sum and the sum and the difference. And the funniest of all, this little ring with places coming out, they call a rat race. Now, the location of the ports around the circle are fractional wavelengths. Between the A and the sum is a quarter wavelength, the same between the sum and the B, and the same between the B and the delta, and then 3/4 of a wavelength of the radiation that you're doing the sum and difference on between the A and all the way around to the difference. Now, I'm just going to leave to the interested student. In the next 3 view graphs, I go through the logic of how, when a waves come in A and B, indeed the sum and difference come out those sum and difference ports, and I'll just leave it to you to go through the logic if you're interested. But trust me, they create the sum and the difference in just these 2 little pictures. Okay, so what do we end up with? And then we'll finish this lecture, this part of the lecture. What we end up with is, to calculate that error signal, is we take the magnitude of the difference signal, and we multiply by the cosine of the phase between the difference and the sum and the difference that are coming out those 2 channels, and then we divide it by the sum signal, and what we get within the beam width of the radar is a linear line. The amplitude that you get out of this error signal, which is the delta divided by the sum times the cosine of the phase angle between sum and difference, is a measure of how far off you are the center of the beam. And if it's negative, you're off to the left. If it's positive, you're off to the right. And you can see that visually if you just take the ratios of the difference over the sum. These are the magnitudes. And the unambiguous region is right down here. Okay. I've shown you just in one dimension how we do this. We can do it in 2 dimensions. We can have 4 feeds instead of just 2. I showed you 2 side by side for azimuth monopulse. But if you do 4, and from the 4 you generate the sum signal by adding the A, B, C, and D channel. And these are the locations of feeds at the focus of a parabolic dish. And for the elevation difference, you'd take B plus D minus A plus C. And for azimuth difference signal, you'd take A plus B minus C plus D. But in this case, you need 3 receiver channels to process the 3 outputs: the sum, the elevation difference, and the azimuth difference. Okay. Now what I'd like to do is take a brief break now, and we'll come back and discuss phase comparison monopulse in the second part of the lecture.